All right. Welcome to another deep dive, everyone. We love these, just taking some really cool sources that you send us and just kind of digging into them, finding out what's in there.
Yeah.
For you, our learner, this deep dive is about how computers think, I guess you could say, or at least how they represent information and manipulate it at the lowest level.
Yeah, at the very, very bottom, like what's really going on.
Without getting too bogged down in the technical stuff, we want to keep this pretty approachable.
Mm-hmm.
And the stuff that you sent in this time it's pretty fascinating, actually. Excerpts from Introduction to 80 by 86 Assembly Language and Computer Architecture.
Sounds a little intimidating, but trust me, it's super interesting. Like, our goal here is to uncover those core principles of how software actually talks directly to the hardware.
Right.
Get ready for some aha moments. I think we're going to have a lot of those today.
I think so, too. And, we know our listeners are coming from all different levels of technical background. So Don't worry. If something like 80 by 86 just sounds like, I don't know, some ancient artifact, we're going to keep this fun and engaging.
Totally.
All right, so let's break this down. Our source material kind of starts by taking a look at, like how we view a computer, right? Because there's all these different perspectives.
Right, absolutely.
Most of us, like just as everyday users, we're interacting with applications,
Right.
Your web browser, your music player, whatever tools you use for work.
Yeah.
That's kind of our world.
Exactly, yeah. And then you have programmers who, they see the computer as like the platform to build new software,
Right.
to make those very applications that we use every day.
Exactly. And then for a programmer who's working in like a high-level language, something like, I don't know, Python or C++ or something,
Yeah.
the compiler, like, kind of creates this image of the computer for them, right? Where it's like, dealing with whole numbers, decimals, text, storing these in named places in memory, running through lists of instructions, doing calculations, all those kind of familiar programming ideas.
Yeah, absolutely. And then here's where it gets really interesting. What our source really digs into is that the actual computer operates at a much more fundamental level, right?
Right.
Like, this is the architectural level, the world of machine instructions, which is what the CPU, the central processing unit, like the brain of the computer, actually understands. It's like, this is the language it speaks.
Right. It's like a translation almost.
Exactly.
From that high-level code that you write. Eventually, it's converted, sometimes through like an intermediary step, assembly language, into these, super basic commands that the hardware actually acts on.
Yeah. And the source even talks about how assembly language itself needs to be translated further into this final machine language.
Right.
And I think it's really cool because, there's a lot of programmers who spend their whole careers working in those high-level languages, and that's totally fine.
Right.
But our source makes this great point, like having a good grasp of these low-level, like machine-level principles,
Right.
it's so valuable no matter what level you typically work at.
It's like understanding the basics of how a car engine works, even if you just drive the car. Right.
Exactly. Yeah, like it gives you a much deeper insight into how things work.
Right. And I think it can make you a better programmer, even at that higher level, if you understand what's going on under the hood.
Totally. It informs the way you approach problems. It can help you write more efficient code.
Absolutely. So what are some of these like core ideas? What are we kind of getting into with this source material?
Well, we start with memory addressing. It's like how the computer actually finds specific pieces of data that are stored in this vast memory space.
Like, there's all this data in there.
Yeah.
But how do you know where to look for the thing you need, right?
Exactly. And then we dive into CPU registers.
Okay.
These are like tiny little super fast storage locations right inside the processor itself.
Mm-hmm.
And, they're used for calculations, holding temporary results, all sorts of things.
And then, of course, there's like the big question of how a computer represents information at all.
Right.
I mean, we see these words, we see numbers, but underneath it's all just patterns of ones and zeros.
Right. Absolutely. Yeah. Like our source takes us through all the different ways that computers can code numbers, text.
Yeah.
I mean, this is the heart of it.
So let's start with those numeric formats. We're talking about binary, which is the absolute bedrock, right?
Yeah.
Just using 0 and 1.
Right. Yeah, it's the foundation of everything. And then there's hexadecimal, which is like a more convenient shorthand for those long binary strings. And of course, we have decimal, our everyday system.
Right. Good old base 10.
Exactly. And then there's octal, which you might see sometimes in, more specialized contexts.
All right. So our source kind of points out that they're careful about using these little
Oh,
subscripts
yeah.
to indicate which base we're talking about, right?
Yeah.
So like a little 10 for decimal, a little 16 for hexadecimal.
Yeah, it's important to be clear about that.
Absolutely.
Yeah.
And then there's this like really handy trick they share for converting between hex and binary.
Oh, yeah, that's a good one. Because, 16 is a power of 2.
Right, 2 to the 4th.
So each hex digit actually directly maps onto a group of 4 binary digits.
Okay, that makes sense.
And the source has a really great example. The hexadecimal number 3B8E2.
Okay.
So if you break that down, the 3 becomes 0, 0, 1, 1 in binary. The B, which is 11 in decimal, becomes 1, 0, 1, 1. 8 is 1, 0, 0, 0. E, which is 14, is 1, 1, 0. And then 2 is 0, 0, 1, 0.
Okay, so you're just substituting those 4-bit patterns for each hex digit.
Exactly. So that 3B8E2 in hex is, well, 0, 0, 1, 1 space 1, 0, 1, 1 space 1, 0, 0, 0, 0 space 1, 1, 1, 0 space 0, 0, 1, 0 in binary. I'm just putting those spaces in there so it's easier to read those long strings.
Makes sense, yeah. All right, and then they also talk about octal, which is base 8. And because 8 is 2 to the 3rd power, each octal digit corresponds to, a group of 3 binary digits this time.
Exactly.
And then converting to decimal from octal, that involves multiplying each digit by a power of 8.
Right. Yeah, it's similar to how you do it with hex and powers of 16 or even decimal and powers of 10.
Right. It all follows that same pattern.
Yeah, it's a nice pattern.
Now, moving beyond just numbers, computers also need to represent text.
Right. Yeah, that's crucial.
I mean, how else are they going to, display all the amazing things on our screens?
Exactly. And that's where ASCII comes in, right?
Yeah. So tell us a bit about ASCII.
Okay, so ASCII stands for American Standard Code for Information Interchange. And it's basically the standardized system, right? It assigns a unique numerical value to each character. Like all the upper and lowercase letters, digits 0 through 9, all the punctuation marks, even some special control characters that tell the computer to do things.
Okay.
Like start a new line or something. And the source mentions that it uses 7 bits. So that allows for 128 different characters.
Okay, not a huge amount, but enough for the basics.
Right, yeah. And then another interesting thing is that these ASCII codes are often given in hexadecimal, even though, deep down they're binary.
Right, kind of like we were talking about earlier, just a more compact way to represent them.
Yeah, exactly.
Now, our source makes this kind of important distinction between the ASCII representation of a digit and its actual binary value, like when the computer's doing math.
That's a really important point. Like, for instance, the character 2 in ASCII is represented by, hexadecimal 32.
Okay.
But the number 2, when you're, when the computer's doing calculations.
That's going to be represented by the binary pattern 10, right? So computers use both. ASCII, mainly for handling like text input and output, displaying stuff on the screen, reading what you type on the keyboard, and then the direct binary representations for all the internal number crunching.
That makes a lot of sense. It's like having 2 different ways of encoding the same basic information, depending on what you're trying to do. And then there's also like some pretty neat patterns in the ASCII standard.
Yeah. There's some really clever stuff in there.
Like how the upper and lowercase letters are arranged numerically.
So they did this on purpose, right? Like the ASCII codes for all the uppercase letters, they're all grouped together.
Okay.
And same thing for the lowercase letters. And then there's this consistent difference between the code for an uppercase letter and its corresponding lowercase letter.
Oh, interesting.
Yeah, it's very organized. And that actually makes like certain text manipulations in code much more straightforward. I see. Okay, so that was, kind of intentional.
Yeah, they put some thought into that.
Now, our source also talks about these ASCII control characters, which they kind of sound like, I don't know, relics from the typewriter days.
Yeah, they kind of are. But they're still totally fundamental, like even today.
Really?
Yeah, to how text is processed. Like carriage return, that's often abbreviated as CR.
Okay.
And it has the hexadecimal code 0D, and it basically moves the cursor back to the very beginning of the current line.
Like all the way to the left?
Yeah, exactly. And then line feed, which is often abbreviated LF, has the hex code 0A. And that moves the cursor down to the next line, like hitting the enter key on a typewriter.
Right. So those two often work together.
Exactly. Like when you press enter on your keyboard,
it
usually sends both a carriage return and a line feed.
Okay, so it's a 2-part command.
Yeah. And that tells the computer to go to the start of a brand new line.
I see. That makes sense. And our source mentions you can use them independently, too, if you need, like, fine control over the cursor.
Yeah. Yeah, absolutely. Like if you wanted to stay on the same line after you've prompted the user for some input, you could just use the carriage return.
Okay, so it gives you that flexibility.
Exactly. And they also mentioned some other control characters that you might see,
Okay.
like form feed.
Mm-hmm.
That's hex code 0C, and that traditionally told a printer to, like, advance to the next page.
Oh, interesting.
Yeah. And then horizontal tab, which is hex code 09.
Okay.
That moves the cursor over to the next tab stop. Backspace, hex code 08.
Okay.
That moves the cursor one position to the left,
Right.
usually deleting the character that was there.
Mm-hmm.
And delete, which is hex code 7F.
Okay.
And it's interesting, both backs and delete are used to, like, get rid of characters.
Right, yeah.
But they actually generate different ASCII codes.
I see. Interesting. All right, so that's characters represented by ASCII. Now, what about numbers that we want the computer to actually do calculations on? How are integers represented in the system?
So when it comes to representing integers in the, Intel 80 by 86 world,
Right.
the source highlights some common lengths of binary numbers that the architecture works with.
Okay.
We've got the byte, which is 8 bits,
Mm-hmm.
a word, which is 16 bits,
Oh.
a double word, that's 32 bits,
Mm-hmm.
and a quad word, which is 64 bits.
Okay, so it gives you a range of sizes to work with.
Exactly. And, the size you use depends on how big the numbers are that you need to be able to handle.
Makes sense.
And they give a really nice example.
Okay.
They take the decimal number 697
Okay.
and show its 16-bit binary representation, with all the leading zeros, to fill those 16 bits.
Right.
And then they convert that into its hexadecimal equivalent, which is 0 to B9.
Okay.
It's the same value, just, more compact and easier for us humans to work with.
Right, that hex is really coming in handy here.
Oh, yeah, it's super useful.
Now, representing positive numbers, that's,
Yeah.
pretty straightforward in binary.
Mm-hmm.
But what about when you need to deal with negative numbers? That's where 2's complement comes in, right?
Exactly. This is like one of those really clever techniques that makes computers work.
Okay, so I've heard of 2's complement, but can you kind of break it down for us? Why is it so important?
So 2's complement is all about representing signed integers, both positive and negative,
Okay.
using binary. And it does it in this really efficient and standardized way.
Right.
The source kind of describes how to find the 2's complement of a number. You invert all the bits, flip all the zeros to ones and ones to zeros,
Yeah.
and then you add 1 to that result.
Okay, sounds like a specific recipe.
It is. And the really cool thing is, why do we do it this way? Well, it has some significant advantages over other methods, like signed magnitude,
Okay.
where you use 1 bit for the sign and the rest for the magnitude, or 1's complement, where you just flip all the bits.
So what are those advantages?
So with 2's complement, you have a unique representation for 0, which is great because it simplifies the hardware.
Oh, okay.
And it also gives you a slightly wider range of negative numbers for a given number of bits.
So you can store more negative numbers, basically.
Yeah, like for an 8-bit system, 2's complement lets you represent numbers from negative 128 up to positive 127.
Okay, that's pretty impressive.
Yeah, it's very efficient. And the source also briefly mentions 1's complement just for contrast, which is, like we said, just flipping all the bits. So 2's complement is definitely the more widely used method.
Okay, that makes sense. Now, let's talk about binary coded decimal, or BCD.
All right.
It sounds like it's for representing decimal numbers, but in a different way than just converting them directly to binary. Is that right?
Exactly, yeah. BCD takes a different approach. Instead of converting the whole decimal number to binary,
Right.
it represents each individual digit with its own group of 4 binary bits.
Okay, I think I'm starting to see how that works.
Yeah. Like, let's say you have the decimal number 123.
Go.
In BCD, the 1 becomes 0001, the 2 becomes 0010, and the 3 becomes 0011.
Okay, so it's like a direct mapping, 1 decimal digit to 4 binary bits.
Exactly, yeah. So the whole number, 123 in BCD, is represented as 0001, 0010, 011.
Okay, and how about if you have a bigger decimal number, like with more digits?
It just keeps going. Each decimal digit gets its own 4-bit binary group.
Okay.
The source uses the example of 3,691.
Okay.
And in DCD, that would be 001 for the 3, 0110 for the 6, 1001 for the 9, and 0001 for the 1.
Okay.
And on a PC, each of those 4-bit codes might be stored in a whole byte. So you might see that BCD representation of 3,691 as like the hexadecimal sequence 33, 36, 39, 31, with each byte holding the BCD code for one digit.
I see. Okay.
And they also mention fixed-length BCD representations and packed BCD,
Okay.
where you can actually fit 2 decimal digits into a single byte
Oh, wow.
if you need to be really efficient with storage.
It's like cramming them in there.
Yeah.
All right. So it sounds like BCD might be really handy for, things like financial calculations.
Absolutely, yeah. Anywhere where you need to avoid even tiny rounding errors.
Right, because those can add up quickly.
Yeah, it's a big deal in finance. Now, we've talked about whole numbers,
Right.
but what about numbers with the decimal point? That's where we get into floating point.
Okay, yeah. So how do computers deal with those?
So floating point is how computers represent numbers that aren't whole, or at least very close approximations of them.
Okay.
And the source points out it's closely related to scientific notation.
Okay, I remember that from, like high school science classes and stuff.
Exactly. You have the significant part of the number, an exponent that tells you the power of 10, or in binary, the power of 2 to multiply by, and a sign to say if it's positive and negative.
Makes sense. And they even give an example of converting the decimal number 78.375 into the IEE single precision floating point format, which is 32 bits long.
Yeah, they don't get too deep into the conversion. It can get pretty complicated. But it illustrates that these decimal numbers with fractions, they get translated into a specific binary format.
Okay.
And what's really important to understand is that it's tricky to represent these real numbers with a finite number of bits.
Right, because you can have these infinite decimals and stuff.
Exactly. So because of that, you can get tiny inaccuracies or rounding errors when you're working with floating point numbers, which is something programmers need to watch out for, especially in those long calculations like simulations or graphics.
And if those tiny errors keep accumulating.
Things can get messed up. All right, so we've covered how data is represented, but now where does the computer actually store all this information? That brings us to memory organization.
Okay, so imagine the computer's memory as this huge collection of individual slots.
And each of those slots can hold a single byte, which is 8 bits of data, right? That could be instructions for the computer to follow or the data those instructions are working on. And every single byte in this memory has a unique number called its address.
So it's like a giant numbered list of bytes.
Yeah. It starts at 0 and goes up to, well, a really big number depending on how much memory you have.
Makes sense. And our source mentions these memory segments, especially in those older systems like the 8086 and 8088.
Oh, yeah, those were the days. So back then, the memory wasn't just one continuous block. It was divided into these logical units called segments.
Okay.
And each segment started at a memory address that was a multiple of 16 bytes.
Oh, okay, so the last hex digit of the starting address was always 0.
Exactly, yeah.
Okay, so if you've got all these segments, how did the processor know where to look for a specific piece of information?
So they use this combination of a segment number and then a 16-bit offset from the start of that segment. So when a program needed to access a memory location, it would usually just store the 16-bit offset. And the segment that was being used was determined by these special segment registers inside the CPU.
I see.
It was a way to manage the memory given the limits of those early processors.
Right, because 16 bits can only address 64 kilobytes directly.
Yeah, that wasn't a lot. But then with the Intel 80386 and all the later chips, they made things a lot easier.
Right.
They switched to a 32-bit flat memory model.
Okay, so no more segments.
Well, they're still there under the hood, but programmers could think of the whole memory as one continuous address space.
Right.
And they could use those 32-bit addresses to access any location directly.
So it was a much simpler model.
Way simpler. And it allowed for way more memory, too.
Yeah, that was definitely a good move.
Oh, yeah, a big improvement.
Now, we've talked about memory, but the real brains of the operation is the CPU.
Absolutely, the central processing unit, yeah.
And it has all these internal components, specifically the registers, right? What can you tell us about those?
So registers are like the CPU's personal high-speed scratch pad.
Okay.
They're these incredibly fast storage locations built right into the CPU itself.
Okay.
Used for holding the data that the CPU is actively working on.
Like what kind of data?
Like the numbers it's adding or subtracting, temporary results, memory addresses, all sorts of stuff.
Makes sense.
And because they're right there in the processor, accessing them is super fast. Way faster than going out to memory.
Okay, speed is key here.
Oh, yeah. Absolutely crucial. And the source focuses on these 32-bit general-purpose registers, EAX, EBX, ECX, and EDX.
Okay, so those are the workhorses.
Exactly. They're used for all sorts of things. And Intel has this convention where the bits within a register are numbered from right to left,
Okay.
starting with bit 0 as the least significant bit.
So it's like the opposite of how we normally write numbers.
It can be a little confusing at first, but you get used to it.
And then you can actually access parts of these larger registers as smaller units, right?
Yeah, like the lower 16 bits of EAX can be accessed as the AX register,
Correct.
and the lower 8 bits of AX are known as AL, and the upper 8 as AH. So it gives you flexibility to work with data of different sizes.
I see. Very efficient.
Yeah.
And the source gives this example of using the sub-instruction to subtract 10 from the AX register.
Yeah, that's a common operation.
Now, beyond these general-purpose registers, the source also talks about ESP, the stack pointer, and EBP, the base pointer. What are those all about?
So these are all about supporting like how programs are structured.
Okay.
So the stack pointer, ESP, it holds the memory address of the top of the stack.
Okay, what's a stack?
The stack is this special area of memory used for temporary storage, especially when you're calling procedures or functions. You can push data onto the stack and then pop it off later.
Okay.
And the base pointer, EBP, is often used to establish a fixed reference point within the stack frame.
What's a stack for?
It's like the area of the stack used by a specific procedure.
Okay.
And EBP makes it easier to access parameters and local variables within that procedure.
All right, so it helps keep things organized.
Yeah, it's all about structure.
And the source mentions they'll cover the stack in more detail later on.
Yeah, there's a lot more to say about stacks.
And what about those segment registers like CS, DS, and SS?
Right, so we talked about those in the context of the segmented memory model. In those older systems, they held segment selectors.
Okay.
But the source clarifies that in 32-bit protected mode, which is what modern operating systems use,
Right.
these segment registers actually hold selectors that point to segment descriptors.
What are those?
They're these more complex data structures that contain the starting address and size of the memory segment.
Oh, okay.
But the good news is that in the flat 32-bit model, this is all handled behind the scenes.
Okay.
Programmers don't really need to worry about the details of segments.
Those abstracted away.
Exactly, yeah. It makes life a lot easier.
There's also the instruction pointer, EIP. That sounds important.
Oh, it's super important. EIP holds the memory address of the very next instruction that the CPU is going to execute.
Like a bookmark.
Exactly. It's always pointing to the next thing to do. And the source mentions that assembly language programmers can't directly change EIP.
All right.
The CPU itself manages that, incrementing it as it fetches instructions.
So it's like automatically moving to the next line of code.
Exactly. And when you have a jump instruction or a call to a procedure, the CPU updates EIP to point to the new location.
Okay, that makes sense. And to speed things up, the CPU doesn't wait for one instruction to finish before starting the next, right? That's propelining.
Exactly. Pipelining is like an assembly line for instructions.
Okay.
The CPU can be decoding one instruction, fetching the operands for the previous one, and executing the one before that, all at the same time.
So it's doing multiple things in parallel.
Yeah. It's a huge performance boost.
Now, finally, there's the flags register, often called E-flags. What's that all about?
So E-flags is like a collection of status bits called flags that reflect what happened during the last operation.
Okay, like indicators.
Exactly. Like the carry flag, CF, is set if there was a carry or borrow in an arithmetic operation.
Okay.
The parity flag, PF, tells you if the result has an even or odd number of ones in its binary representation. The zero flag, ZF, is set if the result was 0.
Okay.
And the sign flag, SF, tells you the sign of the result.
And these flags are used for making decisions, right?
Yeah, exactly. Like you might have a jump if 0 instruction that only executes if the 0 flag is set.
Okay, so the CPU can change its behavior based on those flags.
Exactly. They're like little decision-making helpers.
All right, now the CPU and memory are essential, but a computer also needs to interact with the outside world, right? That's where I/O devices come in.
Absolutely, yeah. Input and output is how the computer communicates with us.
So what are some examples of I/O devices?
The source lists some common ones, like the keyboard, the mouse, the monitor, disk drives for storage.
Makes sense. And how does a programmer actually talk to these devices, especially at the low level of assembly language?
So at the very lowest level, each device has its own set of addresses or ports in what's called the I/O address space.
Okay.
In the 80 by 86 world, there's a whole 64 kilobyte range of these I/O port addresses.
Okay, so it's like a separate address space just for I/O.
Yeah. And a device might use several ports for sending commands, receiving data, and reporting its status.
And these are separate from the memory addresses we talked about earlier.
Totally separate, yeah.
It sounds like it could get really complicated trying to keep track of all those port addresses.
Yeah, it definitely can. And the source emphasizes that programming I/O directly at this level is really difficult.
Okay.
You need to know a lot about the specific hardware.
Right. It's not for the faint of heart.
No, not really. So a common approach is to use procedures, which are like pre-written chunks of code,
Right.
and handle all the low-level stuff for you.
So it's like a layer of abstraction.
Exactly. So instead of directly manipulating port addresses, you might call a procedure that takes like a character as input, and it handles all the details of displaying that character on the screen.
And then you can build even higher level procedures on top of those.
Yeah, absolutely. Like one to print an entire string of text.
So it's all about layering those abstractions.
Yeah, to make it manageable.
Now, all this amazing hardware needs software to tell it what to do.
Right.
Right. And that's where the operating system comes in.
Absolutely. The OS is like the conductor of the orchestra.
Okay.
It manages all the resources like the memory, the CPU, the I/O devices, and it provides a platform for other programs to run.
And what were some of the early PC operating systems?
The source mentions PC-DOS and MS-DOS.
Okay, yeah, I remember hearing about those.
They had this command line interface where you typed commands to interact with the computer.
So it was all text-based.
Yeah. The OS would display a prompt, and you'd type in commands, either built-in DOS commands or the names of programs to run.
And then later on, we got graphical user interfaces like Windows.
Yeah, those were a game changer.
But that underlying command line stuff was often still there.
Yeah, sometimes hidden away, but still there.
Now, if you're writing assembly language code, you need a way to actually type it in and save it, right? That's where text editors come in.
Absolutely. Text editors are the programmer's trusty tool for creating and modifying plain text files.
Yep.
And these files are just collections of ASCII codes representing the characters you type.
Makes sense. So your assembly code is stored in a text file.
Exactly. The source mentions some of those old school text editors like Edit and Notepad.
Right.
They were pretty basic, but they got the job done.
So you write your assembly code.